And section 1.5, this is very short. Right, the rough idea of section 1.5 is the following. We know that C is a field, which means certain algebraic operations on C, we have either axioms or have proven, depending upon your point of view, that the elements of C satisfy those properties. We also know that R is a field, which means that the elements of R satisfy exactly the same algebraic properties, which means that elements of R and elements of C can be put together and combined and used in exactly the same way. So this means algebraic techniques that you've used in R will work in C perfectly fine. Results might be different. I mean, you've just seen with the exponential function that results are different. But the justification that that e to the z exists for all z, the proof of this is very, very similar to the proof that, and that's because the algebraic portions of those proofs are exactly the same. It doesn't matter what field you were working over when you did those proofs because the algebraic rules transfer. So what this means is the normal manipulation of equations works fine. Okay, so here's an example. F of z equals z to the n minus 1. Well, f of 1 is equal to 1 to the n minus 1 equals 0. So by the normal standard manipulations in, for example, R, we can say that this what is it? Yeah. So by the normal standard manipulations, we know that that is equal to this. And you've proved this when Z is in R, but in previous courses. But the proof that this gets written out as that only relies on the algebraic properties of the elements of R. And R is a field. And the algebraic properties of fields kind of the same. The rules are the same. You multiply things together and you can switch elements of things, and distribution works the same way and all sorts. So this works just as well in C as it does in R. Right, here's another example. Z minus alpha, Z minus beta equals Z squared minus alpha plus beta, Z plus alpha beta. So for example, we could have Z squared minus 2i, which implies that minus 2i is equal to the product of two things. And I just happen to have made a guess. 1 plus I times negative 1 plus I is equal to minus 1 plus 2i. Then we have I times I, which is minus 1. The minus 1's cancel, and you get minus 2i. So one of alpha is one of these, and one of beta is one of those. So we can say that z minus 2i is equal to z minus 1 plus I, and z plus 1 plus I. We could even go a little further. Wow, a little further. A different way of maybe writing the same thing is say 2i divided by 1 plus I equals 1 plus I. Now that certainly looks a little odd to me, because you wouldn't have, this kind of thing doesn't happen in the real numbers, right? So the results will sometimes be odd and different from what you expect. But normal manipulations all work. Another example, long division of polynomials is fine. It's page 5. Okay, so let's just do the result I just showed you before. Z minus I plus 1 divided into z squared, and there's no z to the power of 1 terms. I'm going to put the 2i over here. Okay, what do I times this by to get z squared? Has to be z. That goes there. z, because its power is 2, power is 1. Z times z is z squared. Sorry. Z goes there. Z times z is z squared minus z times that, 1 plus I, and then we subtract all of that off. The z's cancel, and we get zi plus 1 minus 2i. So what do we times z by to get this? We times it by I plus 1. So I plus 1 times z is z I plus 1, and I plus 1 times minus I plus 1, as we just worked out. It's minus 2i. Subtract all of that off, 0. Long division, and because the remainder is 0, this implies that z squared minus 2i is equal to z minus 1 plus I, z plus 1 plus I. If you are unfamiliar with long division of polynomials, talk to us at the tutorial. Go see someone at PASS, student support, the Dan fellow who came in. Go talk to someone about it. Anyway, that's section 1.5.